I'll provide you with the recording. I make them usually unlisted YouTube videos, so you have to have the link to watch it. So it'll just be for you, and you can then rewatch the session to go over anything that you missed or want to review. And we'll take a break about halfway through today. That's a good stopping point. So I'm Kurt Menke. I work at Septima. I'm a GIS consultant, and I do a mix of spatial analysis and some cartography and teaching, obviously. I'm a QGIS certified instructor, so you will get a certificate with this course. There's two kinds of QGIS certificates. There are participation and there's completion, and this is a completion certificate. So I'm going to be giving you an assignment to complete during after this first session, and then a second one after the second session, where you basically just have to take a couple specific screenshots that show that you completed the exercise. And when you turn those both assignments into me, then I'll send you your certificate at the end of the course. And also an OSGeo charter member. And I thought it would be nice. Oh yeah, I have this slide too. I meant to put this at the end, but since it's here, I'm also a QGIS author, and last year was a busy year for books for me. A Dutch colleague of mine, Hans van der Kwast, and I finished the second edition of QGIS for hydrological applications. And that book deals with quite a bit of raster data. And we use raster data in that book for some specific workflows around delineating catchments, hydrological catchments, and then Strahler order stream channels from elevation data. So that's a great book for a specific application of raster data. And the one on the right, Discover QGIS 3X, was just published in August, the second edition. And that has several exercises dealing with raster data as well. This is the course schedule. The most important thing after today is next Wednesday, we'll meet for an hour. And this is a chance for you to just ask questions about anything that came up during your assignment, or specific questions you may have about workflows that you are doing with raster data. So just a chance for us to have like an informal chat about raster data. And then we'll continue Thursday with the second session. So I thought it might be nice now to just go around and quickly introduce yourselves. Only one of you, I think, answered the questions I'd sent out. So if you want to quickly just kind of give me an overview of what I asked, like kind of what your background is, what you use QGIS for, how long you've been using it, and what you hope to get out of the course. So I think I'll just start at the top of the list here. Christian?
Yeah, I'm Christian Andersen. I'm a geologist by profession, but I've worked with the LiDAR laser scan products for quite a number of years. I work at the RailNet at the moment with geodata and mostly laser scan data.
Great. Let's see. And Kristen?
Yes, my name is Anne-Christine Eland, and I work at the Danish National Archives, and I'm responsible for preserving geodata for the preservation format for geodata. And we know a lot about vector data, but raster data is not our specialty yet. So I'm taking this course, and I have a lot of questions. I just didn't have time to send them, but I will ask them along. But I can see you will answer a lot of them in your course, I guess. So basically, I'm interested in knowing what's inside the raster format, what's in the bands, how do I see how many bands are in a raster format, and of course, how do I work with the information and the pixels, and I know this is what this course is about, so I'm really looking forward to learning that.
Great.
Yes.
And we won't specifically be working with multi-band rasters in this course,
no,
but we can.
But the elevation model, I'm very interested in that. Yeah, just to get a feeling of what is this and how does it differ from RGB raster? What is the difference between the grid file format and the image format and so on? Is there a difference at all? Yeah. And
Okay,
I've had a QGIS course before, just an introduction, so I don't use it a lot, so I'll get that out of this as well and up brush on that. Yeah.
fantastic. Okay, this is Jonathan.
Yeah, I live in Sweden, Gothenburg. I work as a surveyor / civil designer. So I'm an accidental QGIS user, as many I've noticed. A need for knitting together data and clipping and transforming and gathering data. It's been a good tool, but I can see there's good potential. I've looked at YouTube at your videos and Hans' videos about like stream analysis, and I've used on some projects, but I just want to learn more, like have a more another tool in my toolbox, and also a little bit more see how like a professional like you would work with the data or set up projects, and you just a workflow like the excellent introduction video. So just learning and applying the more skills in QGIS.
Fantastic. Okay, Jakob. Maybe he's see. Oh, here it comes.
I think your microphone is off, Jakob.
Yeah, sorry about that. My name is Jacob, and I'm a business developer at the Danish National Archives. And at the moment, we don't really have the necessary skills to work with geodata, so that's why I'm here to learn a lot about it.
You're in the right place. Good. And Nils.
Yep. I'm a geographer. I work at Septima with Kurt, and I've been using QGIS for over 10 years, I think, but it's mainly been vector analysis and working with vector data. So we had a project in the start of the year using raster data, and I thought I needed a brush up on it, so that's why I'm here today. My version of QGIS is probably a bit old, but it should be within range of working. So
What version is it?
3.22. It's the standard package on Ubuntu.
Yes, that should be fine.
So, yeah.
Okay. So we're going to, I'm going to just run through some of the material in that intro video because maybe not
sorry,
everyone
Kurt?
watched it. Yes.
I didn't get to introduce myself.
Oh, I'm sorry. I didn't see there. Yes, please.
I also noticed there's one more face than it could fit on the screen. So
Yeah.
maybe that's why.
Okay. Yeah.
But yes, I'm Laura, and I'm also a geographer. I work at the Danish Agency for Planning and Rural Development, where I have gathered a little bit of knowledge within vector data and an even smaller amount of knowledge within raster data. So I'm just looking forward to learn more.
Great. And thanks for coming forward. I didn't mean to skip you there.
No problem.
So we're going to look at some of the slides that I started out with just to make sure we all understand everything here. So generally, when we're working in a GIS, we're trying to represent parts of the world with data. And there's two main kinds of data that we can think of: discrete data and continuous data. And discrete data are considered those things that are individually distinguishable. So a tree. And Christian, could you mute yourself? Christian, could you mute yourself? I think your conversation was bleeding through.
Oh, sorry.
Thanks so much. So discrete phenomena, examples of that would be a river, a road, a tree. So data doesn't exist between observations, or another way of thinking about it, you're You're either in the road or you're not in the road. Whereas continuous spatial phenomena are everywhere. So every part of the landscape has an elevation, for example, or a temperature or precipitation that happens when it rains. So these are considered continuous phenomena. And the vector data model is really best suited for discrete objects, points, lines, and polygons. So this is what a lot of us start out using, and I think it's probably used much more widely than raster data because it incorporates a lot of the urban infrastructure that we all work with. But the raster data model is very useful and powerful as well. So the raster data model is composed of pixels or cells, and you can, in a GIS, represent anything as vector or raster. So, for example, we may have vector points, and we could rasterize those and end up with those in a raster format where every point takes up 1 pixel. And you could do the same with line features. And of course, you end up with this stair-stepped pixelated view of things, especially if you zoom in close enough. And that's because rasters have a resolution. We'll talk about that. So there are many types of raster. One kind of continuous raster you might consider as an air photo or a satellite image. There's also land use. This would be like a categorical raster. Maybe categorical is a better word than discrete for this slide. So this is where land use has categories of forest, urban, water, and these are all represented by numeric values in a raster. So it ends up looking like a polygon data set if you're zoomed out far enough, but you can represent this quite well with the raster as well. Another continuous raster would be elevation, which we're going to work on today. And then another example of a categorical or discrete raster might be rasterized roads. And so there's a number of reasons for working with data in one model or the other. So why use rasters? Well, they're obviously better at storing some kinds of data, elevation or imagery, aerial photography. You can represent elevation as vector, so you could use contour lines, for example, but it's much more efficient to use raster data for that sort of information.
Could I ask a question?
Mm-hmm.
Because the elevation model you also mentioned in your introduction, you could also visualize the elevation model in curves.
Mm-hmm.
Is that rasterized something, or is it an image of the presentation of the vector data? How do you know, is this vector or raster?
Well, we can, when we get into working with QGIS,
it looks like an image.
I can, yeah, when we get into working with QGIS in a few minutes, we can just look at layer properties and it will tell you if the data set is vector or raster.
Okay.
So that's not difficult in the software to determine. Yeah.
Great.
So rasters are really efficient for analysis. So we're gonna, in this class, work on a site selection analysis for a potential vineyard. And it's very fast and easy to combine rasters representing different factors for that analysis and add them, subtract them, multiply them together. And so that can be often quite a bit faster than doing the same thing in the vector data model. The maybe the downside of using rasters is that you have this issue with raster cell resolution. No matter how fine you make your pixels, you still are showing an area as a square pixel that has some size to it. Whereas, for example, if we're using points in the vector data model, points take up no space. It's simply an XY position on the landscape. So it's very precise. Also with rasters, as people want higher and higher precision rasters, the data gets exponentially larger. So raster data can take up quite a bit of hard drive space. And the last one, as I mentioned in my video, you can't store multiple attributes. So we're going to see today that you can now in QGIS have an attribute table associated with a raster data set. So raster resolution is simply the dimensions of the pixel in ground units. So it's typically given in meters. And you can see that as you increase resolution from 10 meters down to 5 meters, you end up with 4 times the number of pixels. So the data set gets quite a bit larger. So we call the 30-meter resolution would be a larger resolution. The 5-meter resolution would be the smaller resolution or finer. So this is a screenshot of layer properties from QGIS for a raster data set, like the one we're going to work with in a few minutes. And so here in the main information tab of layer properties, you get a lot of information about the extent of the raster. The width and height is in pixels. The data type, the driver, what kind of format it's in. So and this would be the same kind of information you get if you're looking at a GeoPackage vector layer or a shape file. There would be a driver or a file format for that vector data set. And there are even more formats for raster than there are for vector. And people use them for various reasons, but we can we'll be working with the most commonly used format in this class, which is the GeoTIFF, which is the one that's being shown here. So there's several raster data types. There's signed and unsigned. Signed simply means it can hold negative values below 0. Unsigned can only use positive values. And then you have integer versus floating point. So integer is obviously whole numbers. Floating point can hold decimal places. So a categorical raster like land use is typically going to be an integer data set, and one that stores elevation is typically going to be floating point because you need more precision for that. And then you can combine these and you end up with a whole series of raster data types that QGIS can read. And these are kind of divided into the bit length of them. So an 8-bit raster can hold 256 values. And so they'll range from 0 to 255 for an 8-bit unsigned with no negative values and no decimals. Integer 16 and unsigned integer 16 are 2 very common formats. So as you go up in bits, you're just able to store more values in that raster. And we get down into the floating point rasters that can hold decimal places and get to store quite a large array of different numbers within them. So when we, let's say, export a raster and we're going to save a copy of it, we can choose which type of raster we want that to be. So in this class, we're going to be working on a site selection analysis for a potential vineyard in Denmark. And we have these different criteria. One involves land use, that the land has to be considered grassland or cropland. One has to do with products we derive from elevation data. This is slope and aspect. Slope is how steep a slope is. Aspect is which direction of the compass the slope is facing. And we can derive both of those from elevation data. We also need the vineyard to have a specific soil type. And we're going to get that from a polygon data set. And then we're also going to have a minimum size for the potential area. So below 1.7 hectares, our customer thinks it's too small. So these are what we're going to use to identify potential sites in a study area. If you downloaded the course materials and unzipped it, it'll look like this in the course data folder. There's a folder for the land cover data sets. There's a folder for OGC services, which I'll talk about here in a minute, and then a styles folder with a couple QGIS style files, which are UML files, and we're going to load one of those this afternoon and see how that works. And then there's a couple geo packages that we'll work with. So the sources for the data today, we have a land cover data set that is fairly new. This ESA world cover data set was just released in December of 2021, so it's still quite new. And it has 10-meter resolution. For the elevation, we're going to be using Denmark's height model, which has 40-centimeter resolution. So again, the resolutions of these two rasters are quite different. So we're going to identify something in the middle there to work with for our analysis. And then we have a soils data set from QGIS, which is Polygon. So in terms of the elevation model, we have two main families of these. We have a digital terrain model, which is the bare earth. It doesn't include any of the trees or the buildings or fences and things like that. And then we have a digital surface model, which does include, as you're seeing here on the screen now, buildings and forest and things like that. So we're going to look at both of these today for our study area. And for sources of a DEM, there are many sources. They can come from ground surveying, differential GPS measurements. In the old school days, stereo photogrammetry, the same technique when there's more than 60% overlap between air photos can also be done with photogrammetric software much more efficiently now. Digitizing contour lines, even more old school. And then what we're going to be working with is LiDAR derived elevation data. There's also radar interferometry, which is what the space shuttle used. So there are some global elevation data sets, and one of those is the data from the space shuttle missions. So in Denmark, we have much higher resolution data than that, but if you're working outside of Denmark, this can still be a decent source of elevation data. So we're going to start working with some OGC services first. So just to make sure everyone understands what these are, you may have heard of WMS, which is a service that provides, basically serves an image of a map. And so QGIS is the client in that scenario, and it requests the map via a URL, and it gets returned to QGIS. And this is really good for background maps or aerial photography and things like that. But you don't actually, in that case, if you're bringing in aerial photography this way, you don't get to interact with the actual data. It's just useful for a background map, and you can't change the symbology of it. We then have WFS, which is for vector data, web feature service. And this serves the actual vector data to your client, QGIS in this case. And so you then have the ability to save that vector data locally as a file-based data set or into a database. You can change the symbology and do any kind of analysis with it that you do with any other vector data set. And then we have WCS, and this is web coverage service, and this is kind of the WFS equivalent for raster data. So this again serves a raster data set to QGIS, but a raster data set that's geo-referenced and has all of the attributes or bands in it. And so you can then save this locally and use it in an analysis. So this is how we're going to pull in elevation data into QGIS. So today's workflow, we're going to start with the digital terrain model, and we're going to extract it to our study area. We're going to bring in land cover data, and we're going to extract that to our study area. And then we want these two data sets to align. And one of the things we're going to do as we extract them is put them both at the same spatial resolution. So they're both going to be, in this case, 2 meters of resolution. So the DTM is going to come in at 40 centimeters, and we're going to convert it to 2 meters. The land cover is 10 meters, and we're going to downscale it to 2 meters. So they'll match. But you'll notice when we do that, the pixels won't be perfectly aligned between those 2 data sets once we do that. So there's a tool in QGIS to make sure that the pixels line up perfectly between a series of rasters. And that's important because we're going to later on next week start combining these for our analysis. And in that scenario, you want all those pixels to align. So we'll end up with these aligned rasters that cover our study area. We're then going to generate slope from the DTM and aspect. And then we're going to reclassify all 3 of these. And so this basically means that we're going to take them and say, okay, we have all these slope values from, 1 to whatever, 60 or something degrees of slope. And we're going to break this into meaningful areas of slopes, something that means something to a vineyard. So there's going to be a specific slope threshold that's going to be ideal for our vineyard. And so we're going to weight that the highest. We're going to reclassify these all from 1 to 4, with 4 being ideal conditions for slope, 1 being the worst conditions for slope. And we'll do that for all 3 of these. So we'll have these weighted versions of each one of these that we can combine into our analysis. So as with most analyses, all of this data preparation is most of the work. I think I'll save part 2 for next week and start our demo here. So I'm going to get out of PowerPoint and into QGIS. So I am working with QGIS 328, the current long-term release. And we're going to start with some elevation data. So we're going to, in the course folder, I have a WCS XML file inside the OGC services folder, and it contains a couple URLs in there. And so this URL here is the one for the Danish height model. And it has 2 products in there, terrain and OFLL, which is the, basically one is the terrain, one is the digital surface model. And the way you use this URL is first you copy it out of the XML file. And then you, in QGIS, switch to your browser panel. And the browser panel shows you all of your different data providers along with your hard drive. And there's a data provider for WCS. So to add a new data provider, you simply right-click on WCS and you choose New Connection. And you simply paste the URL into this box and then give it a name. The name can be anything you like. So you can call it Danish height model or anything that you prefer. The name isn't so important. The URL is the important piece. Then you click OK, and you'll be connected to that service. So I'm already connected to it. I have this connection here. So, and you'll see there's 2 layers in here. If I right click on this and go to edit connection, you can see the URL that's in there from that XML file. And so now I can simply right click on one of these and add it to my project. So I can right click and add the terrain to my project. And we have our terrain. And if we look at our layers panel, this is the default symbology for a single band raster, which is this gray color ramp with the highest value being white and the lowest value being black. And if I open up my layer styling panel by clicking this little paintbrush button, this layer styling panel will show you that this is the single band gray renderer right here. So this is the digital terrain model, and I'm going to also add our study area here. So I'm going to go into in my hard drive and find our course folder, raster data, course data. And if you don't know this little trick in QGIS, this is helpful. Oftentimes our data is several directories deep on our hard drive somewhere. And in QGIS, you can right click on a folder and choose add as a favorite. And it will then add that folder as a favorite so that you can easily get to it. And I can rename this favorite to raster course data. And now I have my raster course data easily accessible. And if I look in here, there's a geo package called vector data, and in there is a layer called study area. So I'm going to drag and drop study area onto the map. And I'm going to switch to my layers panel and right click and zoom to layer so that I'm zoomed into that study area. Okay, so the height model doesn't look so exciting with these default settings. We're going to make a pretty nice visualization of it here in a second, but let's explore the data a little bit. First of all, when you right click on a vector data set, you get things that you're probably pretty familiar with, like open attribute table, zoom to layer, show feature count, all these sorts of things, layer properties. If we right click on a raster data set, you get a slightly different context menu. There's, for example, zoom to native resolution. And that'll zoom to the pixel resolution of the data set. If I right click again, there's also stretch using current extent. So we're not seeing much in this image right now because the data is being stretched from black to white across all of Denmark, across from the highest point to the lowest point in the data set. And so in this small study area, there's not much variation, at this scale. But I can tell QGIS to stretch using the current map extent, and it will then stretch this data from black to white just to my current map extent. And so I get much more information about what's going on when I choose that option. I'm going to go back and zoom to my study area. And I could again stretch using current extent, and it will stretch it to the extent of zoomed into my study area. If I right click and open up properties for this layer on this information tab, I'm going to see the URL that I used to pull this in. The provider is WCS, the Web Coverage Service. And I see the extent of the data set, the width and height in pixels. So it's quite big. It's a float 32. So that means that it's floating point. So it stores decimal places, and it's 32 bit. So it holds quite a bit of different data values in it. It tells you a little more about the WCS version. If I scroll down, it'll tell me the coordinate system. And down here, we can see that it's a single band image. So elevation data is always a single band image. That when you'll have multiple bands is when you're working with satellite imagery, where you may have, up to 10 or 12 or more bands to work with. And in that scenario, in the layer styling panel, you could tell QGIS to use different band combinations to see different things in the imagery, but we don't have that here. I can show people an example of that next week during the question and answer session. But we can see that it's a single band.
Can I ask one question here?
Mm-hmm.
How do I know what's in the band? If I don't know that I download the elevation model, how do I know that this is heights?
Well, that's a good question. I mean, that would go for almost anything you added to QGIS. You could add a polygon data set, and how do you know that's ion-DOM boundaries or what have you?
But is there any metadata in the raster format that could tell us that?
Yeah, there is. Let me see if I don't think QGIS pulls this in automatically. The WCS service doesn't bring it in a way that QGIS can parse it anyway, but the name of the data set is DEHOM terrain.
Yes, so you
that's
can.
one indication of what.
And
the
how
data
do you
set
know
is.
that it's in meters? That, yeah, it says down there, actually units, meters, but
Yes.
that's the coordinates. But this is the height, so you just need to have some metadata outside the file telling you then that in this raster file, the height is in meters and not in kilometers or centimeters.
Yeah, I've never seen a data set outside of the United States that wasn't in meters for the
So it's
Z
always in
units.
meters. Yeah.
Yeah.
But you need to
So,
know that.
of course, yeah.
Yeah,
You know,
okay.
that's the kind of thing you'd have to check with the source to be sure. In the US, a lot of elevation data products are in feet. Outside the US, they're almost all in meters. So that's something you can usually count on.
Okay, thank you.
Let's see, there's also a histogram tab here. So we can compute the histogram for the data. And it's kind of difficult in here to see. Let me see if I can reload that. But we get a lot of the values kind of down here at the low end of the spectrum. I'll show you some better histogram tools in QGIS later in the course. There's also an elevation tab. This is something that has been added at 3.2.8. So if you're using 3.2.2 or an older one, this would be a new feature, and it's not required for this course. But this is something new for basically telling QGIS that this data set represents an elevation surface, and so you can tell QGIS this, and this will help when we. I'm going to show you a new feature later in the afternoon of an elevation profile that QGIS now has built into it, and so that has to do with that new feature. So that's kind of what you get. The other tabs will be kind of similar to vector data. The source tab is going to have the coordinate reference system. There's a symbology tab, etc. Over here in the layer styling panel, there are some settings for rasters for, by default, when you add a raster to QGIS, basically to save memory kind of guesses at the minimum and maximum value in the raster. But you can force QGIS to get the precise minimum and maximum in this min-max value settings section here of the layer styling panel. So if you expand this, you'll see that the statistics extent is the current canvas here, and the accuracy is the default of estimate. So you can see in our canvas, it ranges from 49 to 1.87, and I can choose to make this actual, which it tells you is slower, and it will update that. But it looks like it was already, didn't change anything, so it was already it was fine. And that's probably because when I right-clicked on this and chose stretch to current canvas extent, QGIS read that at that point. Okay. Just checking my notes, make sure I don't miss anything. So what we want to do here is make this a local file. We don't want all of Denmark for our analysis. It's more than we need. We just need the data for this small study area. So since this is a WCS layer, I can export it to a local raster. So I'm going to do that by right-clicking. Oh, and I think QGIS is still trying to calculate the maximum. It's not responding. I may start another instance of QGIS here. I'm not sure how long this is going to take, and I can quickly catch up. So I'm going to add the terrain. And the study area. Okay, so on this terrain layer, I can save it by right-clicking on the layer and choose Export, Save As. And here we can see that the 40-centimeter resolution of this data set. And one of the things I'm going to do here is change this to 2. I'm going to upscale it so we end up with a slightly coarser version of this because it's basically more data than we need in this case. And it'll also make our processing a little faster by having it be 2 meters by 2 meters instead of 40 centimeters by 40 centimeters. And it'll tell you how many columns and rows that will result in. And I'm going to save this to my folder, and I'll call it terrain. This is a GeoTIFF format. So when you do go to save this out, you can choose what format you want this to be in. And I'm just going to keep the default of GeoTIFF. But you can see you have a long list of different formats that you could potentially change this into. I'm not sure why this has happened. In the vector world, you pretty much have 3 or 4 common formats: shape files, geo packages, maybe flat GeoBuff, maybe PostgreSQL, but most of your data is going to be in one of those. In the raster world, there are a huge number of formats for different applications and different agencies, and the GeoTIFF is probably the most commonly used, so we're just going to stick with that. So here, by setting the resolution to 2 meters by 2 meters, that will resample it up to 2 meters. The other thing we need to do is specify the extent. So we're going to choose the study area extent. So that will force it to export just the part of the raster that is within the study area boundary. And with that, we can click OK. And QGIS will export this out. It doesn't take terribly long. I can turn off the original one, and now I have this local file-based data set. So I can see that this is on my local file system now is terrain.tiff. And I can see that it has, if I go down to the resolution, I can see that, where is that? Yeah, you can see it's not exactly 2 meters by 2 meters. When you export a raster in QGIS, sometimes it'll be close to the resolution you specify, but not perfect. And we'll be able to fix this when we use that align raster tool. So it's very, very close to 2 by 2, but not exactly. And that has to do with the coordinate reference system. So now I'm going to open up my layer styling panel again. And I'm going to show you some of the renderers we have to work with in QGIS. First off, since this is terrain, instead of single band gray, I can choose hillshade. And this will render this data set as a hillshade image. And let me just show you the difference if I was to add the other terrain data set, the overflow, which is a digital surface model. And if I bring that in and style that one as a hillshade, you will see that you get in the digital surface model all the buildings, forest, fences, hedges in there. And that can be quite nice for certain applications, but we're really more interested in getting a bare earth model. So we're using this terrain version where all of that is stripped off. But both are available. You can also see here that you're starting to get some gridding in here. It's not very smooth. And this is kind of an artifact of this hillshade renderer that's rendering it as this hillshade image where it's telling you the sun is coming from the northwest and it's 45 degrees above the horizon. You can change these settings, but this is the default. And interestingly enough, you know, it's impossible for the sun to be in this position. The sun can't be in the northwest at that altitude. It's always from the south. But when generating a hillshade, this is the direction that creates something that's most intuitive to the human eye. If you put the sun on the other side of the 180 degrees to the other side of the compass rose, you'll start seeing peaks as valleys and valleys as peaks, and it becomes very disorienting to many people. So this default setting is what works for most. This Z factor is a setting that's set to 1 because our X and Y coordinates are in meters and our Z coordinates are in meters. So since they're all in meters, the Z factor is 1. Where I grew up in the United States, where we have X and Y in meters and Z in feet, we have to put a conversion factor in there to put the Z into the same coordinates as the X, Y. So that's why that's there in case you have to do that, but most of the time we do not. And then to fix this problem with the striping that we're seeing, we can go down to this resampling section. And by default, QGIS uses this nearest neighbor resampling for zoomed in and zoomed out. And if we change this to bilinear, it will smooth the raster and take that away so it looks a little nicer. Okay, so we have our terrain styled nicely as a hillshade, and we can take this a step further. I'm going to right click on this and duplicate the layer. And I'm going to rename this copy colored terrain, just so I can keep it straight. So it's the same data. I just have another copy of it now. And if you're not used to working with this layer styling panel, the reason I'm using it instead of going into layer properties and working with the symbology tab is that if I make changes in this symbology tab, well, first off, it covers my map, so I can't see what I'm doing. And I have to choose my symbology settings and then click OK or apply and see if it did what I wanted it to, and then maybe get back in here and make more changes. Whereas with the layer styling panel, I can do all the same changes to the symbology and styling, and the changes appear on the map instantaneously. It's much handier. So whatever layer you have highlighted here is the one that you'll be working with in the styling panel. So you have to make sure you're working with the right target layer here. And if selecting it doesn't change it like this, you can always just click the drop-down menu and choose the correct layer that you want to work with. So it always is good to make sure you're working with the right layer. So here, I'm going to change the colored terrain from the hillshade renderer to this other renderer, single band pseudo color. This basically lets me use a color ramp to have a colored elevation data set and color it from lowest to highest elevation. And it will use kind of a random color ramp when you first use it. And none of these in here are specific for terrain. So we're going to use a catalog that comes with QGIS instead of any of these in our list. I'm going to go down to create new color ramp. And we get this color ramp selector. And we're going to choose this catalog CPT City, which ships with QGIS. The gradient option would let you design your own color ramp in this color ramp designer, where you choose the start, the beginning and ending color, or any intermediate colors. but we're going to use this catalog because this catalog has a whole bunch of color ramps that you can add to QGIS, and they're all organized by category. So here's this color ramp selector. So you can see there's color ramps for bathymetry, precipitation, temperature, and then there's this category for topography. So these are all designed for showing terrain. So I'm going to choose this one SDA, kind of like that, and I'll click OK and click classify. And now I have my terrain styled with a nice earth tones. Now, if I turn on my hillshade above that, it obscures the one below. And the old school way of making a nice color hillshade would have been to go to this next tab here, transparency, and knocking the transparency down so that I can see the color of the layer below. But it's kind of faded. I don't get all the full color. I can make it a little more transparent and I start seeing the colors a little bit better. But then I start losing a lot of the detail in the hillshade at the same time. So instead of using transparency, we're going to use another fantastic set of tools in QGIS, these things called blending modes. So below here, we have layer rendering and this blending mode section. And you'll see there's a whole series of blending modes in here divided into these categories. And this is the lighten group. This is the darken group, the contrast group, and then I forget what they call this one. But we're going to use this one called multiply. This is probably the most commonly used blending mode in QGIS, and this is the reason people use blending modes the most, is to create this kind of color hillshade effect. So by applying the blending mode to the topmost layer, it blends it but with this multiply algorithm with whatever is beneath it. So we get all the detail in the hillshade and all the colors at their full saturation in the colored terrain below it. So we can quickly make a really nice rendering of the terrain doing that. And we can take it one step further by making another copy of this. So I'm going to duplicate the terrain one more time. I'm going to move this one above. And I'm going to rename this contours. So this contours layer is, our map gets darker because I now have two hillshades on top of the colored one. So it darkens the map quite a bit. I'm going to switch this from hillshade to contours. And I'm going to switch the blending mode back to normal for this. And we don't see anything because the default contour interval is 100, which is a little big for the elevation in our study area, which only ranges by about 40 meters. So we're going to choose a contour interval of 2. So now we see the contours on the map. And the index contour is always 5 times the contour interval. So we'll make this 10. And the index contours just allow you to read the contour map a little bit better by seeing where the elevation changes every 5 contour lines. So we can change the symbols for each of these. So we're going to change the index contour symbol by clicking on this bar. And it's simply a line symbol now, and we're just going to make it a little thicker. Up, click this a few clicks. So the index contours are a little thicker. So that's nice. We zoom in, we can see we're getting a nice image of the terrain, and this shows us the slopes a little bit better. But we can also use a blending mode here. So we can use a different one like overlay. kind of softens those contours and kind of gives them the color of the color DEM that they're running through. Soft light is another nice one. So with that, we have a nice terrain map, all using the same layer, just using 3 copies of it and using the different elevation renderers that we have in QGIS. So once you know how to do that, it's, you know, you can make a nice looking terrain map in a few minutes once you've done it a few times. I do have a slide on those blending modes here. So as I mentioned, there's a lighten group, a darken group, which is where multiply is, the one we used first. And it says pixel values of the top item are multiplied with the values for the bottom item. We also, in the contrast group, tried overlay and soft light. So you can read about those. And so these are there throughout QGIS. There's a lot of different ways you can use them. So sometimes you have to just try them to see what they do. You can get some very strange looking maps using some of them with some data sets, but sometimes they really create some magic. So they're worth exploring. Let me see. See, we are just about top of the hour. Let's take a quick break and we'll come back at 10 after. So you can get some coffee and we'll come back at 10 after. I'll pause the recording and I'll probably stay here. If you have any questions, you're welcome to ask questions, but we'll take a quick break. And I'm going to show you a new feature that's landed at 328 that is pretty exciting, and it's related to terrain that we're looking at. So if I go to the view menu here, and I'm in QGIS 328, there is this now an elevation profile option here. So I can click on this and it opens up this elevation profile panel down here. There is this option now to make this undockable. It's kind of a free floating window, which is kind of nice. They've done this for the 3D viewer as well, which we can look at. And so if I want to get a slope profile of a line in here, I'm going to go into the properties for my colored terrain data set here, this layer. And I'm going to find the elevation tab in layer properties and tell QGIS this represents an elevation surface. And then I can choose a style for how I want the elevation profile to appear in the panel. So I can make it be a line or fill below. And if it's fill below, I can go in here and choose a different style. So I can make it look like the elevation itself by switching from the simple fill to gradient fill, and then choosing a color ramp. You know, I'm gonna go back. I forgot to show you something that's important here. So here, I'll repeat that. When I imported this color ramp from CPT City, if I want to use this again, it's quite straightforward. I can just click here and choose Save Color Ramp. And I don't want it to be a project style. I want it to be default, so it's available in all my QGIS applications. And I can give this a name. I can call it terrain. And then I can choose a tag. So maybe I'll have a tag in my style manager now called terrain. And if I click add to favorites, it'll show up in this first list when I click here. So I'll click save. And now when I click down, I'll see that terrain is available here as color ramp for me to use, so I don't have to import it again. It's just there. So now to repeat those steps, I'm going to go into layer properties here, and I'm going to choose for this layer the fill below profile chart appearance. I'm going to click on this symbol, and I'm going to use, instead of simple fill, that gradient fill. And I'm going to choose a color ramp, and I'm going to choose the terrain color ramp that I just saved. And I'm going to invert it so it's going from highest to lowest, and click OK. So now I'm going to go back and again open up my elevation profile panel. And here I can, if I had a vector layer like roads, I could get the elevation profile of that road crossing the terrain. That would be using capture curve from feature. But here I'm just going to draw a line on the map. So I'm just going to choose capture curve, and I'll just draw a line across this area here. Right click to finish. Why isn't? Oh, forgot somehow the check mark for representing elevation surface became unchecked. Let me draw my line again.
I don't get it either. I just followed along here, but it's blank in my.
Yeah, that's what happens when you do a live demo sometimes. Okay. Yeah, it's not working. Well, I don't want to spend too much time debugging it. I'll show you next week. Normally it's really cool, but not so much today for some reason. So yeah, we'll skip that. But this is the only time it hasn't worked for me, so I'm a little surprised. Usually it generates a really nice elevation profile. But moving on, we're going to add the land cover data now. So I'm going to go to the browser panel and find this folder for land cover in the course data. And there's 6 basically tiles that cover Denmark. And I know it's this third one down that covers our study area, N54E12. So I can add this to my map. And I'll drag it to the top. So it comes in styled. This is has different land cover classes associated with it. And in the metadata for this layer, it tells you what the different colors represent. And we'll get to styling that so that we can understand what the different categories are. I know green is forest. That one's pretty straightforward. But we're going to clip this to our study area the same way we did with elevation. So I'm going to right click on it and choose export, save as, just like I did with the DTM. And I'll save this into my output folder and I'll call it land cover. I'm again going to choose my study area as the extent. This is also in a different coordinate system. So I also have to reproject this into UTM like the rest of my data. And I'm going to put the resolution at 2 by 2. Since this one was in a geographic latitude, longitude coordinate system, it had strange cell sizes, 9 and 4. They were not square, and that's simply because it's coming from an elliptical coordinate system, and we're now going to reproject it flat. And we're going to choose the same resolution we did for the DTM. So with that, I can click OK. And I can export it. And one thing you can do quickly is right click on this original one, go down to Styles, Copy Style, and right click on the new one and go Styles, Paste Style, so that symbology comes through to this extracted one. So I just right clicked and extracted that. So I did the subsample, the reprojection, and the clip all in one operation. By exporting it, you can set all of those aspects. But there are other ways to do this. We had to use this technique with the WCS layer, but since this one is a file-based data set, the land cover, I could have also gone to the raster menu and chose extraction and clip raster by mask layer. And then I would have simply chosen the original land cover. The mask layer would be study area. I could choose the target CRS. This one is rather a long dialog box, and then save it out to a file down here. This is basically a GUI for the Google Warp command line tool. So you get the syntax for the same Google Warp command line that you could run to do the same thing. If you ever want to play with those tools that come with GDAL and learn those command line utilities, when you use some of these tools in QGIS, it gives you the command line equivalent. So this is another way to clip a raster in QGIS. And again, it wouldn't work with the VCS service, but it works with a file-based raster like this land cover. So I don't need to do that since I've already clipped it to my study area, but I wanted to show you can do that as well. Another thing is, in this land cover, there are these 6 different tiles that cover all of Denmark. And if we were doing some kind of analysis across all of Denmark, then we would be in a situation where we need to mosaic all these tiles together. And so we see in Windows Explorer the thumbnail previews of those land cover data sets that cover all of Denmark as tiles. And if you need to do that, you can go to the raster menu to miscellaneous. And there's this option to build virtual raster. And this is a really fast way to get a mosaic developed from a series of tiles. So I can go for my input layers, and I don't have them loaded. So I would choose this add files option. Go in here and select all those tiles. Click open. So now all 6 tiles are selected. I can go back, 6 inputs selected. And then I can simply save this to a VRT. The output would be a VRT file. So for example, I could save this to my course folder as land cover. And it'll save it as a VRT file. And if I click run, it's very fast, and it immediately creates a mosaic of all those tiles that would cover all of Denmark and southern Norway and Sweden. And then if you wanted this as a single data set, you can right click and export it out as a new data set. So that's usually quite one of the fastest ways to mosaic a bunch of tiled rasters together. They often come that way. Another way to do that is going to miscellaneous merge. And merge is another algorithm that takes a bunch of tiles, but physically merges them into the final output. So either one of those workflows would work to produce a single raster from a series of tiled inputs. I will remove this since I don't need it and go back to our study area. So if we look at the layer properties for land cover, we can, for example, look at the histogram for this, and we can see that this land cover data set just has categories. It's instead of the values representing something like elevation, they just represent types of land cover. So there's a category 10, 30, 40, 60, 80. So you can see which types of land cover are the most common in the study area, but we still don't know which are which. So we can go ahead and load a style. So I gave you a style, and if I go to the symbology tab here in QGIS, I can load that by going down to this style menu and choosing load style. And in the styles folder of the course data, there's an ESA world cover color legend QML file. And a QML file is just a file that stores symbology that you can export out of QGIS. So I click open and click OK. And now I have descriptions of what each of those represent. Because that I did the work in QGIS earlier to read the metadata and find out what category 20 means and created this symbology. To create that QML file, I simply did the reverse, where I went into layer properties, went to the style menu, and instead of load style, I chose save and saved this out to a QML file. So if you ever want to share a style with a colleague or a customer, you can export out layer symbology that way as a QML file and give it to them and they can load it. And so again, if we go back in here and we go to the information tab, we can again see you have the same issue where it's very close to 2 meters by 2 meters, but it didn't quite end up perfectly 2 meters by 2 meters. So next we're going to use the raster align tool. We're going to go to the raster menu, and we've already now looked at extraction and miscellaneous. And now we're going to look at this tool align rasters. And this is a tool that lets us take in a series of rasters and choose one as kind of the template and have them all align their pixels to that. So there is some resampling involved in this algorithm, but it's quite an easy tool to use. And to start, I simply click the plus button and choose the input raster. So I'm going to basically be aligning the terrain and the land cover. And for terrain, I have the same terrain data as 3 different copies. It doesn't really matter which one I choose because they're all the same data, even though I just have them symbolized in different ways. So I'll choose colored terrain, and I'm going to choose an output file name for this because it's going to create an aligned version of color terrain. So click browse, and in my output folder, I'll call this terrain aligned. And I want to rescale the values according to the cell size. So as this, it's not going to change much because it's already basically almost at 2 meters by 2 meters, and it's going to be close to the original, but there'll be a little bit of rescaling, and I want to make sure that the values are scaled according to the cell size. So I'll go ahead and click OK, and I have my first data set added. and I'll click the plus button again and add land cover. And I'll browse and I'll call this land cover aligned, the output. And again, I'm going to rescale the values. Click OK. So I have my 2 layers here. It switched to contours because I think it's all the same data, and that's the one on top. Like I said, it doesn't matter because it's all the same data. You can choose which one you think is the best reference or the reference layer. I'll just choose contours in this case. And I want to check cell size down here and make it an even 2 by 2. And this tool will definitely produce output that is an even 2 by 2. The CRS is fine, that's already set. And so I can click OK and close. And now if I go into the properties of this aligned layer, I can see the pixel size now is a perfect 2 by 2. And it's 3171 by 1782. And if I check the terrain aligned, it should match 3171 by 1782. And it's also 2 by 2. So we now have 2 sets of rasters that are perfectly aligned, which is what we want for our analysis. And I can, I don't need to style these because I'm just going to use them for the analysis. If I was going to make a map, I can just keep the original ones, and you wouldn't really see much difference between the 2. I don't think if I, the changes would be subtle, but I could copy the style for this and paste it here and see if you can see small shifts. If I zoom into the data a little bit, you'll see that there are some small shifts in the data as it aligned, but they're not big enough that you'd noticed on a whole map.
Do you mind reminding us why we're aligning them? Is it that the raster calculator needs them to be exactly the same, or?
Yeah, exactly. We're gonna next week, the next stage of when we get to the real analysis, we're going to be using this raster calculator to mathematically combine these rasters together. So we want the pixels to align so that we're adding one pixel to another. You don't want to be in a situation where one pixel is getting added to a junction of 2 or more pixels in the other data set. You want them to be aligned. And
the tool that we use, the align raster, how does it actually?
Well, it takes a reference layer. So I chose, in this case, the first thing I added was my reference layer. So the reference layer for when we ran this was the terrain. So it basically takes the terrain as a model, and it forces it first makes that an even 2 by 2 meters, and then it scales the other raster land cover to match it exactly.
So those they need to be clipped to the same size, or what would happen if they're not clipped to the same mask or clipping layer, or it doesn't work then, right? It depends on that they're actually like a border is the same or something like that. I'm just trying to understand what it does.
Yeah, well, for this workflow, the best practice is to clip everything to the region that you're working in, and then get all the rasters in the same coordinate system, the same pixel dimensions, and then align them to make sure that they are all perfectly aligned. So it's those are usually the steps that you do in order. So we took care of the projection and the pixel size, but when we exported them, and then we had to align the rasters to make sure that the 2 data sets had pixels that were perfectly aligned. So that's one of the things you want to look for whenever you're using the raster calculator to combine 2 or more rasters. It's best that they are like that. You don't really want to be in a, you can, it'll, the tool will do it, but from an analysis point of view, it's more sound to have everything lining up and at the same resolution. You don't want to be adding a raster that has 40 centimeter resolution to one that has 10-meter resolution. It doesn't really make sense. So usually for an analysis, you're going to choose a pixel dimension that meets your needs in terms of detail and also matches what you have available for input data. But that's something you have to carefully consider when you're looking for data sources for different things that you want to represent in the raster data model. So does that make sense?
Yeah, thank you. Yeah, that makes sense.
So another new feature that will hopefully work here is that there's now in 328, there's a plugin that was developed so that you can create a raster attribute table. And so here, we didn't talk about this renderer. So we've used hillshade, contours, and single band pseudo color. And the single band gray was what the terrain came in with by default. And here we're using this other one, paletted unique values. So this is the renderer that you use when you're working with a raster that is categorical, that has categories of things like this. And so it gives basically every unique value a color, and you can change that. So now in QGIS, you can also open up, basically create an attribute table from this. And so some raster data sets, like vegetation data sets, will come with an attribute table. This one doesn't have one, but I've installed the plugin here. If I go into plugins and search for raster attribute table, you'll find the plugin for raster attribute table, which I've installed. So you can install that in QGIS. And it will appear if I right click on this layer. I have in my context menu the option to add a new attribute table. It doesn't really make sense to do it for the terrain because it's a floating point raster with a huge number of different variables or values. But for a categorical raster here that just has 7 or 8 values, it can be handy. So if I choose new attribute table, I can choose either one of these formats, a GDAL auxiliary XML or a sidecar DBF, and click OK. So it has created it, and now I can open the raster attribute table. So it took in how I have the data classified. It has a color column with those colors and a class column with the descriptions of each land cover type. And it has the original value as well. And it also has the count. So even from this, we can see which is the least occurring land cover type, shrubland, and which is the most common grassland by the pixel count in our study area. So this is a nice feature that you have now for rasters in QGIS.
Can I just ask, is this attribute table, is it inside the geotiff? Is it because it, or is it a file beside the geotiff?
It's a file because I chose
Yes.
a sidecar
Yeah, you chose
DBF.
the other one, but you can make it inside of the file, or
If you
it's
make
there.
it,
Yeah.
I think if you make, I think it creates just an XML file next to it. I still think it's a sidecar file.
Yeah.
It doesn't embed it in the data.
Okay.
But this is the DBF that I just created
Yes.
for my land cover.
The DBF. Yeah. Thank you.
And in here, It acts like
Can
a
I-
normal attribute table. I can put this into edit mode. I could add additional columns to it. So I could, for example, add another column that classified these in some other way. And then I could use that to reclassify the way the data looks on the map. So I might, I could, for example, add a column here. General purpose field, and I'll give it a name. I don't know, just making something up here. Type, and I can choose where that goes. Actually, I'm going to make it integer and click OK. So now I have didn't do it. The QGIS gods are not with me today or something. Let me try it one more time. Try class name and type, and after that. That's strange. That might be another thing I've tried. I've used this before where I can add a column, and then I can go in and I can calculate values, and then I can reclassify the way the data is symbolized based on that. So it's a handy feature. And I should show you that in if I bring in QGIS 3 open. Yeah. In QGIS 330, the very latest version of QGIS, let me copy this layer and paste this into QGIS 330 here. QGIS 330 doesn't need the plugin. This attribute table functionality is just built into QGIS. It's part of QGIS core by QGIS 330. So I might actually try it here. I can open the raster attribute table. Let me see if it would let me add a column here. Yeah, there. In 330, it's working. So I could go in here and I could break this into, type A and type B, maybe some type C. Like that. And now I could choose type as a new classification field and classify. And it now classifies my data into A, B, and C for those classes I just entered. So you can use it for things like that, which is really handy. We're going to look at other ways you can reclassify next week, but that's now part of the core in QGIS 3.3. And it's really useful for these kind of data sets like land cover. So that brings us here to almost near the end. I could go ahead and generate the slope and aspect real quickly, and then we'll pick up next week with the rest. So to generate the slope and aspect, I would open up the processing toolbox. And in here, you'll find a raster terrain analysis section. And there's tools, aspect. There's a hillshade tool for creating a hillshade raster on disk from a terrain data set. Hypsometric curves, relief. Some of these are very similar, and slope. So let's start with slope. It's a very simple algorithm to run. It just requires an elevation layer, the Z factor, which is 1 because X, Y, and Z are all in meters. And I'll save the output as slope. And I don't want it to be a VRT, I want it to be a geotiff. Okay, so I have the tool set up and I can click run and close. Let me drag it to the top so we can see it. And now we have slope for the study area. If I look at the values, use the single band pseudo color renderer for this. So we can make sure we're using all the values. And it's not really showing us a lot of variation, but we do, you can zoom in and see that there are where the steeper slopes are. You choose different color ramps, red, yellow, green, and invert this so that the steeper slopes are red. That looks a little more interesting. And you can choose different modes here too. So I could choose quantile, which would force it to break out the slope values into a series of classes. So you get a little more detail. So you can see the steep slopes and the flatter slopes. So this is a big lake here, and this is a lake. So we can see some of those flat areas, and then we can see where the hills are. And with this, we can even bring up our terrain, which was using the hillshade renderer, and put that over slope, and it starts to make a little more sense when we can see the hillshade and the slope together with a blending mode like that. You can see the steep slopes. And now we can try aspect. So aspect is going to show the cardinal direction that a slope faces. Let me bring up this slide here to show you this. So aspect is going to be a raster that has numeric values from 0 to 360, depending on the direction that the slope faces. So south-facing slopes would be 180, east-facing slopes would have a value of 90, and so on. North gets 0 and 360, depending on how close it is to true north there. So with this, I'm going to end up styling it with a circular color ramp. Since it's a circular phenomenon, we can style the data so the south-facing slopes get a warm color, the north-facing slopes get a cool color, and we can see the result. But we'll be able to use this to identify moderately facing, south-facing slopes for our vineyard. So again, we're going to choose land cover as our colored terrain as our input layer, and save this out to aspect.tiff. You always have to be sure to choose the right input. If you don't pay attention and you choose slope as the input or something else, you'll get very strange results. So make sure one of the terrain layers is your input.
Good. Just a question. Now you're using the color terrain, but shouldn't you use the aligned terrain for that?
Oh yeah, actually, I was going a little too fast, and you're absolutely right. So I can just remove this, and I think I probably should have done the same for the slope as well. So let me, a quick way when you make a mistake like that in QGIS is go to the processing menu, and you can go to processing history. And I can simply open up like the slope tool, and I can see how I ran it. And I can say, oh yes, I really need to have used terrain aligned for that. And I can just rerun the tool with the correct input. And I can do the same for aspect. So there's the aspect tool I ran, double click on it, make sure I'm using terrain aligned, and run again. Thanks, Nils. I'm glad someone's paying attention there.
We didn't plan this, just saying.
Yeah. But that's a good use of the processing history too, because you can always, if you forget what you did or if it doesn't look right, you can always go back to this history and see exactly what it is you ran to make sure you had the settings correct. And it's also just another quick way of maybe making one modification to a tool and rerunning it. So this is what how QGIS shows the aspect when it comes out. Looks a little psychedelic. But I have an aspect QML style file that I can load for this. Just like I did with land cover. This aspect circular color ramp QML file. Click OK. Still looks psychedelic, but now the south facing slopes are yellow and the north facing slopes are blue. And if I click on this color ramp, you can see how I designed it with both ends being blue. So this would be 0 and 360, 180 being south, 270 west, 90 east. And if you want to save this color ramp once it's loaded, you can do it the same way. Go down here and save the color ramp as a default color ramp, and you can name it aspect. And maybe you tag this also as terrain, add it to favorites. So now I have both of these color ramps available for future use. So next week, we're going to start to reclassify these three inputs, terrain, aspect, and land cover, into meaningful categories for locating a vineyard. And then we'll be using the raster calculator to combine those as we work towards identifying those suitable sites. Please interrupt me with questions if you have them, but I do want to point out that there are some other really nice plugins for raster processing tools. QGIS has a nice suite of them, but there's also this open source software called PC Raster. This is out of the Netherlands, and it has a lot of processing tools in it. Our QGIS for hydrological book is based on PC Raster now. We use this to delineate watersheds because it has some very nice hydrological tools in here. So it has several hundred tools in here for doing things, and most of it is with raster data. And then there's white box tools, and this is another third-party processing library, and it also has a lot of raster processing tools in here. So there's really no shortage of tools you can use in addition to the QGIS ones from within QGIS for working with raster data.
How do you install PC Raster and Whitebox tools?
The plugins are both just from the plugin manager.
It's just a plugin.
Yep. But with PC Raster, it depends how you've installed QGIS and what operating system you're on. It's quite easy on Windows because you can go into the OSGeo for Windows installer, which is how I've have things set up. So if I go into setup for OSGeo for Windows, get to the section here where I can pick libraries. I can run this setup and I can go into it's in the library section. Let me search. PC. So PC Raster is included as part of the OSGeo installer. So you can go in and install PC Raster to your OSGeo installation on Windows quite easily. Otherwise, you have to install it from the PC Raster website if you're on Mac or Linux. With either of them, once you have them installed, you have to install white box tools as well, but it's a single click installer for all operating systems at this point. And so you go into settings, options, and you go to your processing tools, providers. And so for white box tools, you simply, oh, I thought you had to point it to it. Yeah. Yep. You simply have to point QGIS to the directory where white box tools is installed on your system. PC Raster, it picks up on automatically. So as long as you've installed it via OSGeo for Windows, once you install the plugin, all of the configuration is done and you're ready to run the tools. But I can bring some more directions for both of those next week when we have our chat. So, all right, we got through everything. Are there any other questions? We have a few more minutes.
Yes, I have one question. At the Danish National Archives, we are trying to distinguish between image raster files, georeferenced image raster files with 3 bands RGB, red, green, and blue, and then grid file formats. They can both be stored in a GeoTIFF, but they have different numbers of bands and different values in the bands and so on. Is that a correct understanding of the raster file formats? Would you say that those 2 data formats that we have used here, the GeoTIFF files, are they grid files because they have either a category or a measurement and they only have 1 band? Is that correctly understood? Or do they have the RGB band as well to show the colors? Or is that through a palette? I'm just trying to figure out what's inside this file format here. But what would you say?
From the way I think of the word grid, I think of grid as an Esri format that's similar to a coverage where you have an info folder and the grid folder.
Okay.
I don't think I have one handy. Is that what you're thinking of?
No, and maybe I understand it wrong. That's why I'm asking you, is this correctly understood? But it's when we have to preserve these data. At the moment, we say if you have an image, an orthophoto, for example, it's just red, green, and blue.
Yes.
And we can migrate or convert that to a JPEG 2000 part 1 without any georeference. We would take the georeference out to a GML file. But could we do the same if the raster image has measurements inside? Could we say just convert it to a TIFF baseline 6 or something that is not as complex as the GeoTIFF format? Would we lose information in that process? That's what we are trying to figure out here. So that's why I'm trying to understand what's inside these bands. And if I migrate it to a less rich format, do I lose that information? Do I have to preserve these 2 data sets in a GeoTIFF file format?
Is this for archival purposes?
Yeah, it's for reuse if somebody wants to use this kind of data. But in the future, in 100 years, we might not have the GeoTIFF format. We might have to migrate to other formats that are just as rich or has the same information inside of it. So that's the mission we're on. So I'm just trying to figure out what's inside this GeoTIFF. And
yeah, that's a big question, and I don't even. I mean, there's so many raster formats, and I don't know the details of the construction of the GeoTIFF format but
Mm.
my first thought is that the
Mm.
most basic raster format is an ASCII raster, which is
Yeah.
just a text file.
Okay.
And I would think that would be something that would always be able to be consumed
Yes.
by software. So
Yeah.
that's my thinking. I don't know if
Yeah.
anyone
You
else
also
has any
said
ideas.
you didn't recommend it, but you could make an attribute table with all the heights from the raster image, the cells. That would also be a way to extract the information about the heights to a database of some kind. Because I can't see them when I open my GeoTIFF. Can I click on a pixel and see the height in that pixel?
You can now,
Yeah?
yeah.
Okay.
It's a fairly recent, yeah. Actually, no, it's not that recent. So if I use the identify features tool, I can click on terrain, for example, and get the identify results window up, and it gives me the
Okay.
height of
Identify results.
wherever
Yes.
just like it would with a vector data set. Yeah,
Yeah.
I'm looking at aspect, but I'm clicking
Okay.
on terrain. So those values are all in there.
They are in there, but they're not very visible. Yeah, but I understand now.
Yeah, I mean, it's the
Um,
same with a JPEG photograph of someone,
Yes.
but
But that's just a color value we get there, and
yeah.
uh, yes, yeah,
So
that's
yeah,
what I
like the
need to
attribute
understand.
table for you know, like land cover would be one way to represent that data, but I would
Yes.
also just, you can export a raster in QGIS to an ASCII
Okay, yeah.
raster. Where is it in here? So many formats. So yeah, it ends in ASC. Or am I not seeing it? Oh, there's
JPEG,
a binary grid.
but it's
But in
somewhere.
ASCII, so we can look at that next week, but it's not
Mhm.
difficult to export something out to an ASCII raster, and then you just have it as a text file with an array of values,
Okay.
and the georeferencing information is in there as well, and that might be a useful
Yeah.
format for archival purposes. I don't know.
Yes. Yeah.
But
Thank
don't
you.
you have to make a GDAL console call to make an S3S ASCII raster?
Yeah, well, I think you can export this out to an Esri ASCII raster now. I know you can read them in QGIS. I can't remember if Google will write an Esri ASCII raster or not. Yeah. Yeah, I haven't done that in a while.
But I'm much wiser now. Thank you.
Okay.
Yeah.
Great. So I'm going to be sending everyone this evening a link to this recording and the assignment. The assignment is going to have step-by-step instructions for everything I've gone through, along with links to videos for each task. So you'll have all that available to you to kind of go through what I've done, and just email me the assignment when you get it finished. And I'll see everyone next Wednesday.
So,
Thank
thank
you.
you very
See you.
much.